So let's do inference for distributions. So they're two-way tables. It's another chi-squared test. It just got a little different flavor to it. So there's two lessons. In this one lesson, we'll break it up into two parts. The first test we're going to learn about today, and we're going to learn how to do it, is test for homogeneity. You're going to state the hypothesis. So in this case, does background music influence what customers buy? One experiment in a European restaurant compared 3 randomly assigned treatments: no music, playing French accordion music, or Italian string music. Under each condition, the researchers recorded the number of customers who ordered either French, Italian, or other entrees. The null is there's no difference. Playing music, whatever kind of music it is, has no effect, makes no difference in what you order. The null is there is a difference. So that's the idea of homogeneity. Homogeneity, it means sameness, right? It's like the same. So no difference. There's the same. Playing music, not playing music, there's no difference. The alternate, no, there is a difference. It doesn't say each one's different, just at least one of them is different. Okay, so in this case, they gave us a two-way table of the data. They also nicely plotted some bar graphs, which might help us kind of figure stuff out a little bit. So just looking at it, when they played no music, a lot of other food was ordered, about 35% French, about 15% Italian. When they played French, though, no Italian was ordered. When they played Italian, it did affect the amount of French. Italian wasn't the most increased really there. So just looking at that, it certainly might have an effect. So do the differences in these distributions provide convincing evidence, or is it plausible the background music has no effect? Okay, so we could compare them one-on-one, do 3 or 6 different, tests, but that's way too much work, right? And performing multiple tests would actually potentially give you more errors, type 1 errors for that. So how to do many comparisons without increasing the probability of type 1 error, right? So perform an overall test, see if there's convincing evidence. When the overall test shows there is convincing evidence, you can do a follow-up test to decide which ones are better or having more effect. To find the expected counts, we start by assuming the null is true. So we assume the null is true. There's no difference between playing the music, right? So if the specific type of music that's playing has no effect, the proportion of French entrees ordered should be 99 out of 243. Does it make sense? Or about 40%? Because overall, that's what happened. If you combine all the different music or non-music playing situations, you have 99 French orders of food out of 243. So that's the proportion we expect to be true if music makes no difference. Because there were 84 total entrees with no music, we would expect 84 times that fraction, 99 over 243, or about 40%, and you get a total of 34.22. So that's how many you would have expected to get. And so you can calculate each of those expected using this formula: row total times column total divided by the table total. And I would just write those in the same table. You can see they wrote them in different tables. Those are all the observed values. These are all the expected values. I prefer to write them in the same table, put a slash in each cell, and just put the expected off to the side there. To get that number, 34.22, we did 99 times 84 divided by the total of 243. You should not round expected counts. So it's okay that there are decimal. Observed counts should be numbers, like whole numbers. They should be. Here's the formula again. So if you did that, you get 18.28. In the do step, you aren't required to show every term. I usually show the first 2 fractions plus ... and then the last fraction. Okay. For a class project, okay, sorry about that. So this one, for a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. Subjects who were in the experiment were 100 males from the school. half of the males were randomly assigned to be asked, would you vote for a female president by a female interviewer? The other half of males were asked the same question by a male interviewer. Here are the results. This could be interesting. State the appropriate null and alternate hypothesis. So because this is a test for homogeneity, we expect things to be the same. There should be no difference between the proportion of males who would vote for a female regardless of who asked them the question, right? So let's see what we said for this. There is no difference in the true distribution of response to this question when asked by a male interviewer and when asked by a female interviewer. So there's no difference. What's the alternate? There is a difference, right? So there either is no difference or there is a difference. Homogeneity, sameness. So the null is there's nothing different. It's the same. Show the calculation for the expected count in the male yes cell. So male yes cell would be, let's see, it's the fraction. The row total, which is 69, times the column total, which is 50, over the grand total of 100. And you get 34.5. So 34.5 should be the top left expected value. So I put right next to that 30 there, I put a slash, and I put 34.5. And then I calculate the next one. And so you keep going. That should be the table if you fill it out. So if you do each one, the expected values there. Again, I prefer to put it in the same table, just put a slash and write all those numbers in each cell, each respective cell. You would then plug in to the chi-squared formula, show the first two, ... the last one. So the chi-squared value is 4.25. You can also do that in your test or in your calculator as well. So let's just try this. It's pretty cool, actually. So to do this, you have to store a matrix first. So I'm going to do a 3 by 2 matrix, I believe. Okay, so 3 by 2. So you choose the template key next to number 9. I'm going to say 3 by 2. That does look like the table there. So 30, 39. These are all the observed values, 8, 3, and then 12 and 8. So I'm going to store that. To store that, hit control variable, which is store. And I'm going to call it, well, this is about vote. I'm going to call it vote. Okay, so I had to store my matrix as a word there. So now I'm going to go back to menu. 6, this is a type of test. It is called a chi-squared two-way test, is the name of it. So you choose the variable you saved, and it gives you all the stuff. So it gives you the chi-squared value, 4.2. We just found that one by hand. Degrees of freedom is 2, and the way you get that is, I don't know if I showed you that formula yet, but it's degrees of freedom is number of rows minus 1. So there's 3 rows, to be 2, times number of columns minus 1. There's 2 columns, so minus 1 would be 1. So 2 times 1 is 2. That's where that came from. It also shows you the expected matrix. So if you hit the variable key and go to expect, it tells you all those expected values there in your calculator, which again, very handy for it to do that. Got to check the conditions, of course. First two are the same as always. Just like the last one with chi-squared, all expected counts have to at least 5. And you have to list those somewhere in your paper. Again, I prefer to write them in the table itself. So verify that conditions for inference are met. Okay, so random sample, less than 10%. They asked 100 males from the school. We're assuming that this is a large school. There's more than 1,000 males in the school, so then it would pass that test. So large counts, all expected counts. So if you wrote down, you can see the calculator on the left here. Those numbers are all the expected counts. They're all at least 5, so we are good on that one. You should write them on your paper somewhere. Use the table C to find the p-value, or use your calculator's chi-squared CDF. So let's try that. So if we get a chi-squared value of 4.25, you know, menu 6.5, which is distributions, and we want chi-squared CDF. The lower bound is always whatever the chi-squared value is, 4.25, upper bound infinity. Degrees of freedom is 2, we said. So we should get 0.119 for the p-value. What conclusion can you draw? Since the p-value of 0.119 is greater than the alpha level of 0.05, we fail to reject the null. We do not have evidence that there is a difference in how a person would vote for, whether a male would vote for a woman or not. Assuming the gender of the interview doesn't affect the responses. Oh, sorry, I didn't read the question. Interpret the p-value. I thought it said conclusion. Assuming the gender, the null is true. That's always what you assume for a p-value. Assuming the gender of the interview doesn't affect the responses. There's a 0.119 probability of observing differences in the distributions of responses as large or larger than those in this study by chance alone. What conclusion would you draw? That's what I was trying to say. Because you have a high p-value, we fail to reject. There is not convincing evidence there is a difference in the two distribution of responses to this question, when asked by a male or a female. Technology helps us get this right. So again, we could do that in our calculator. You have to store the matrix, and then you fill out the, all you have to do is choose the two-way test to choose which one that is. You can use your calculator to carry out the mechanics of a significance test on the AP exam, but there's risk. So you want to show those 2 or 3 fractions in the pattern there to find chi-squared. Be sure to name the test since you're not going to write down a formula. And then report the test statistic, which is chi-squared, the degrees of freedom, and the p-value. Putting it all together. Okay, so let's try it. So the Pew Research Center conducts surveys about a variety of topics. Okay, let me read this again. The Pew Research Center conducts surveys about a variety of topics in many countries. In one survey, wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents of Australia, United Kingdom, and in the United States were asked many questions, including the following. Some people say the following things are important for being truly of your nationality. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to this question. Do these data provide convincing evidence at the alpha equals 5% level that the distributions of opinion about speaking English differ for residents of Australia, UK, and the US? So ranked by very important all the way to not important at all in the 3 countries, and there's all the rankings there for you. So you would check the conditions. Do the data provide convincing evidence at the 5% level that the distributions of opinion about speaking English differ from residents of Australia, the US, and the UK and the US? So the null is there's no difference, right? So the null is there's no difference in the true distributions of opinion about speaking English for the residents of the 3 different countries. The alternate is there is a difference, right? Make sure to mention the alpha level. Make sure to name the test, chi-squared test for homogeneity. Check the conditions. Random sample, I think it says they took a random sample. And then less than 10%. So it looks like they sampled a total of 3,463 folks. And that's less than 10% of all the people in those countries. So I think that's less than 10%. Really, to do the To do the expected value, you need to know the expected value. So I'm going to go to a calculator page here first and enter the matrix. So hit the matrix key. I like to go to the key next to number 9, the template key. Choose, this would be a 4 by 3 matrix, I believe. So you put in the number 690, 1177, 702, 250, 242, 221, 713, 40, 28, 50, 20, 13, 30. Oh, I should have looked while I was doing this. Okay, so 690, 1177, 702, 250, 242, 221, 7. Oh, I think I made a mistake there. Okay, that's 40, 28, 50. 20, 13, and 30. Let's see if I got that right. I think I did. So we're going to store that control variable, and we're going to store that as English. Okay, hit the menu key, go to statistics, stat tests, chi-squared two-way tests, and just name the thing. It's called English, the matrix, and it does all the work for you. If you want to see the expected matrix, hit the variable key and choose expect matrix. There's the expected matrix. So now we have all the expected values. You would want to write them on your paper, so you have them, because that's part of the third condition, right? So all expected counts at least 5. If you look at that table there, the expected matrix, all of them are at least 5, so we're good. 1,000 is less than 10% of Australians, 1,460 is less than 10% of UK, and 1,003 is less than 10% of US residents. All of them were random samples from each respective country. That expected matrix that is showing there, we would write that down on our paper. Make sure to write those values on there. Then you calculate the chi-squared statistic. You only have to do the first couple and then plus ... I like to do the last one too. That's typically the way we do it. Show the work for degrees of freedom there. So show the 4 minus 1 times 3 minus 1 is 6. The p-value is very close to 0. It's like a number with 13 zeros before it, right? So it's very close to 0. So you can even say that. And then because the p-value of approximately 0 is less than the alpha level of 5%, we reject the null. There is convincing evidence that there is a difference in the true distributions of opinion about speaking English for residents of Australia, the UK, and the US. So oftentimes, you forget to write the expected values there. You have to show that on your paper to get full credit. That is your lesson for today.